Hello and welcome to the Discrete Mathematics at Tennessee State University in the Department of Computer Science. My name is Ali Sekman. I'm a professor of computer science at Tennessee State University. In this lecture, I'm going to introduce how to prove mathematical statements. This is going to be a basic class. Later in the semester, we are going to see more complex ways of proving mathematical statements. We are going to bring the first four lectures that we discuss propositional logic, we discuss rules of inference, and we discuss predicate logic. So we are going to combine all of them in proving mathematical statements. Let's get started. All right. So actually, this is COM 3010 Discrete Mathematics. This is the last lecture of a series of 5 lectures on logic and proofs. And so far, we have seen propositional logic, propositional equivalences, predicates and quantifiers, and rules of inference. Now we are going to use all of them to use in proving mathematical statements. This is going to be a basic class or basic lecture. Later in the semester, we'll talk about induction and other ways of proving mathematical statements. So what's a proof? A proof is a valid argument that establishes the truth of a statement. So basically, we are going to list of arguments, okay? And we are going to have an argument, which is a list of statements. And once we go step by step from statement 1 to statement 2 and so on, we are going to have a true conclusion, which is going to be the truth of a statement. We will have direct proofs and we'll have indirect proofs, proof by contraposition, and proof by contradiction. So that's basically what we're going to discuss. We'll have direct proofs and indirect proofs, which is we will use contraposition and then contradiction. So what's a theorem? A theorem is a statement that can be shown to be true. And we can show a theorem is true using definitions. We can use other theorems that exist. We can use axioms. What's an axiom? For example, when I say 1 plus 1 is equal to 2, that's an axiom. Axioms are statements which are given as true. And then rules of inference. It is important that we use the rules of inference that we have learned so far. So a theorem is a statement that needs to be shown to be true. A lemma is a helping theorem. That means that can be used to prove a theorem, okay? It's a helping theorem. A corollary is a result that directly follows from a theorem. For example, if you can prove something in general, a special case of that general statement might be a corollary, okay? A corollary is a result which directly follows from a theorem. Sometimes we have propositions which are less important theorems, and those are typically used to prove a larger theorem. A conjecture is a statement that is being proposed to be true. There's no proof, but someone says, this is the conjecture that I have. This is a statement. I propose it to be true until it is proven to be false, or if it is proven to be true. If it is proven to be true, it becomes a theorem. Otherwise, it is false. So theorem, lemma, corollary, proposition, and conjecture. These are like, some of the definitions that you should get familiar. So many of the theorems will have the form P implies Q. For every X in the domain, P of X implies Q of X. That's the form that we are going to mainly use to prove theorems, as you will see. So how do we prove conditional statements? P implies Q. So how do you prove that if you are given, our goal is to prove that P implies Q is true. Well, there are sometimes trivial proofs. Why? If we know Q is true, recall the truth table for P implies Q. This is the premise. If premise is true, conclusion is true, conditional statement is true. If the premise is true, conclusion is false, it is false. If the premise is false, no matter what the conclusions are, the conditional statements will be what? True. So now, if we know Q is true, what is the case? Here, Q is true and Q is true. You see that? If Q is true, P implies Q is also true. So therefore, if Q is true is given, no matter what P is, we can always say that, we can always conclude that P implies Q is what? True. As an example, think about this. If it is raining, this is P, then Q, then 1 is equal to 1. This is Q. Q is always true, right? So if it is raining is irrelevant in this case. If it is raining, then P, then 1 is equal to 1. This statement will be what? True. Okay? So this is called trivial proof. In trivial proof, if Q is true, P implies Q is true as well, regardless of the truth value of P. Vacuous proof. Well, vacuous proof is, again, I remind you that we are trying to prove P implies Q is true. If we know that P is false, for example here, if P is false, as you see, P implies Q is what? True. So if P is false, regardless of the truth value of Q, we can say that P implies Q is true. So for example, here, if I am both rich and poor, this is P, and P is false, then 2 plus 2 is 5. This is also false. But doesn't matter, P implies Q is what? True. If the condition is false, regardless of the value of Q, you always get what? P implies Q as true. This is called vacuous proof. If the condition is false, P implies Q will be what? If P is false, P implies Q will be true. Okay, so we will have a lot of conversations about integers. So let's remind ourselves what's an even, if an integer, what's an even integer and what's an odd integer? If you have an integer which is written as, if you have a number which is twice as an integer, that's an even integer. That means that number is even. If it is 2k plus 1, that number is odd. I mean, this is trivial, right? For example, 22 is 2 times k. You see here, k is 11. So 22 is what? Even. But let's talk about 27. This is 2 times k plus 1, as you see here. That means 27 is what? An odd integer. All right. So we will start with direct proof. In direct proof, we will assume P is true. And then we will show that P implies Q is true. But in order to show P implies Q is true, we are going to use rules of inference, axioms, and logical equivalences so that that Q is true. Okay. Well, here we start with P. P is true. I'm not saying P implies Q. If P is true, we are going to show that Q is true. Okay. So here is a simple example. Give a direct proof of the theorem. Here, this is P, this is Q. If n is an odd integer, then n squared is odd. Let's give a direct proof. In direct proof, we'll say that assume P is correct. That means n is an odd integer. If n is an odd integer, n can be written as 2k plus 1, right? Okay, how about n squared? N squared will be what? 2k plus 1 squared. If you have a plus b, how do you get the square of it? A squared plus 2ab plus b squared, right? So here, this is our a, this is our b. So n squared will be 4k squared plus 2k plus 1. 4k plus 1. It's gonna be, sorry about that. Oh, come on. 4k squared plus 4k plus 1. And this is, in parentheses, 2k squared plus 2k plus 1. As you see, if k is an integer, 2k squared plus 2k will be another integer. Let's call it r. It will be 2r plus 1. As you see here, we started with an n, which was an odd number, odd integer. And now n squared turns out to be what? Odd as well. So that's the direct proof. So this is what it is right here. Here's another example. Let's use direct proof to show that sum of two odd integers is even. Well, this is pretty easy. Let's use another color. Assume that I have n, which is an odd integer, 2k plus 1. Okay. Assume I have m, which is another odd integer, 2r plus 1 for some k and some r. Okay. Now I'm going to add them up. N plus m will be what? 2k plus 2r plus 2. Okay, and then 2 parentheses k plus r plus 1. As you see here, we start with two odd integers, and the sum is an even integer, not odd, obviously. As you see here, let's say this is q, n plus m is in the form of 2q. That means twice an integer. This is an integer, this is an integer. Sum of two integers is an integer, right? So it turns out that this is an even number. In fact, 3 plus 5 is 8. This is odd. This is odd. And obviously this is what? Even. Okay. All right, now we are going to prove that if m plus n and n plus p are even integers. So we have, this is an even integer, this is an even integer, where m, n, and p are integers, then we will show that m plus p is even. And we are going to use direct proof in this case because it's pretty simple. Let's do it. If m plus n is even, that means it is 2 times k for an integer k. If n plus p is even, that means it is 2 times r for an integer r. So if I add them up, what do I get? I get m plus p plus 2n is equal to 2k plus 2r, right? And then I move 2n to this side, m plus p becomes 2k plus 2r minus 2n. That means in two parentheses, k plus r minus n. Since k, r, and n are integers, their k plus r minus n will be obviously an integer. Let's call this integer q. Then m plus p will be 2 times q. As you see, m plus b is an even number because it's twice as an integer, twice an integer. So it's pretty simple, direct proof. Okay, here is another example. Rational number. What's a rational number? First, let's define it. For example, 3 over 5 is a rational number. 8 over 6 is a rational number. Okay, 11 over 3 is a rational number. Or 121 over 256 is a rational number. A rational number can be written as p over q. P is an integer, Q is an integer, and Q is not 0. Obviously, I mean, 250 divided by 0 is not defined, so it cannot be what? A rational number, okay? So Q cannot be 0. By the way, for example, 8 over 6 is equal to 4 over 3, right? So this is a rational number, this is a rational number, the same rational number with different representation, okay? So given the definition of rational numbers, again, a real number R is rational if there exists P and Q such that R is equal to P over Q and Q is not 0. Okay, now we are going to prove that sum of two rational numbers is rational. Okay, we are going to use direct proof to show that the sum of two rational numbers is rational. Well, that's pretty easy. Assume the first rational number is P over Q with Q is not equal to 0. That's our first rational number. And assume that we have another rational number S, and let's say it is divided by m over n, and n is not 0. Okay, we have two rational numbers. And I'm going to add them up, R plus S, that means P over Q plus m over n. And that means Pn plus Qm over Qn, right? And now, what is this? Q is not equal to 0, n is not equal to 0, that implies that q times n is not equal to 0. As you see, r plus s is, this is an integer, r plus s can be represented an integer divided by another integer. That means r plus s is also a rational number. Okay, so that's the proof, direct proof. So now we are going to talk about proof by contraposition. Well, if you recall, contraposition, if we have P implies Q, what was the contraposition of this? Q naught implies P naught. P implies Q is logically equivalent to what? Q naught implies P naught, if you recall this. How do we show that? Let's remind ourselves. If we have P and Q, okay, true, true, false, false, true, false, true, false, P implies Q is true, false, true, true, right? And then Q naught is false, true, false, true. That's the opposite of this column. And then we have P naught. P naught will be opposite of this column. Sorry. Okay, opposite of this column, which will be false, false, true, true. And Q naught implies P naught will be between this column and this column. If premise is false, conclusion is false, Q naught implies P naught will be true. If premise is true, conclusion is false, the conditional statement will be what? False. If the premise is false, conclusion is true, then the compound statement or conditional statement is true, and true, true is true. Now, when you look at here, and when you look here, as you see, they have exactly the same truth values. Therefore, we say what? P implies Q is logically equivalent to Q naught implies P naught. So instead of proving P implies Q, as long as you can prove that Q naught implies P naught, that's exactly equivalent, okay? So that's proof by contraposition. So that's what we're going to do now. Okay, here is the question. Prove that if n is an integer and 3n plus 2 is odd. So here, this is P. Then n is odd. N is odd is Q. Okay, so we are going to prove that it's asking us to prove P implies Q is true. That's what we need to prove, okay? If n is an integer and 3n plus 2 is odd, then n is odd. So I'm going to prove instead of this, Q naught implies P naught, okay? So what is Q naught? Q naught is n is not odd. N is not, a number cannot be both odd and even. That means this is equivalent to n is even. So, okay. And what is P naught? P naught is 3n plus 2 is odd. P is 3n plus 2 is odd. That means P naught will be 3n plus 2 is even. Okay. So if I start with Q naught, and if I can show that P naught is true, okay, then I'm done. Okay. If I assume Q naught is true and then that implies P naught is true, I'm done. So if n is even, that means n is what? 2k for some k. Then what is 3n plus 2? Isn't it 3 times 2k plus 2, which is 6k plus 2, okay? And then if I take in 2 parentheses, 3k plus 1, and if I call this is r, 2r. As you see, if n is even, 3n plus 2 is also what? Even. So we prove instead of P implies Q, we prove Q naught implies P naught. Okay. All right. Here's another example. Well, let me see. Yep. Here's another example. use proof by contraposition to show that if x plus y is bigger than or equal to 2 for real numbers x and y, then x is bigger than or equal to 1, or y is bigger than or equal to 1. So here first let's write P is x plus y bigger than or equal to 2. Okay, and Q is x bigger than or equal to 1. Okay, or y bigger than or equal to 1, larger than or equal to 1. Right? So this is P, and we are asked to prove that P implies Q is true. Okay. So now I will try to do with contraposition. I will prove Q naught implies P naught. Okay. So first of all, what is Q naught? Q naught is the inverse of this. So I'm going to do x bigger than or equal to 1 or y bigger than or equal to 1. I will get the inverse of it. The inverse will be the inverse of x bigger than or equal to 1, and or becomes and y bigger than or equal to 1 inverse. What is the inverse of x bigger than or equal to 1? That is x less than 1 and y less than 1. So this is Q naught. Okay. Okay, what is P naught? It is x plus y bigger than or equal to 2 inverse. That means x plus y less than 2. That's what P naught is. So if I start with Q naught right here, if Q naught implies P naught, then I'm done, because it's equivalent to P implies Q. Okay. Well, actually that's easy. Okay, let's prove it right here. We start with this. That means x is less than 1, y is less than 1. If I add them up, x plus y is less than 2, as you see here. I just directly show that. So that means Q naught implies P naught is true. That means P implies Q must be what? True. Okay, proof by contradiction. Well, we are going to prove if P is true or not. Okay, we are given a statement and we want to prove if that statement is true or not. Okay, in order to do that, we will assume that P naught is true. Let's try to do by contradiction. Let's assume that P naught is true, and we will show that that's not possible. Okay, if we can prove that P naught cannot be true with a contradiction, then P must be true, because a proposition is either true or false. That's basically what we do. Okay. All right. So you assume that P naught is true, and you derive a contradiction for a statement. It doesn't have to be contradiction that P naught is true. You can derive a contradiction for a statement that assumes P naught is true. Okay. For example, if P naught is true, P and P naught cannot be true, right? So basically start with the assumption that P naught is true and derive a contradiction for a statement. For example, you know that P and P naught must be false, right? You know that P and P naught must be false, but when you start with the assumption that P naught is false, maybe we will prove that P and P naught is true, which cannot happen. So that's a contradiction. Okay. So then you will conclude that P naught cannot be false. P naught cannot be true. That means P must be true. Okay. It's pretty simple, actually. Here, use proof of contradiction to give the proof that square root 2 is irrational. Remember rational numbers? Rational numbers are numbers that can be written as P over Q. If R is a rational number, you can write it P over Q. This is an integer. This is an integer, and Q is not equal to 0. I also told you that rational numbers may have multiple representations. For example, 8 over 4 is the same as what? 2 over 1, right? So both of them are rational numbers. with the same representation, but there is a minimal representation of rational number. That means you cannot, for example, 15 over 10 is the same as 3 over 2. This is the minimal representation, okay? So I will assume that, so now we are gonna say, assume square root of 2 is not irrational. In other words, square root of 2 is rational. We will assume that. And square root of 2 has a minimal representation. That means square root of 2 can be written as a divided b, okay? And b cannot be 0. And a and b do not divide each other. So a and b are not multiple of each other. Let's assume that, okay? So in that case, if I get the square, 2 is equal to a square plus b square, right? So that implies that a square is equal to 2b square. This implies that a square is even, because it is twice as an integer, right? If, by the way, if square is even, that implies that a must be even. Think about, for example, any even number. If you take the square of it, that's going to be an even number. That's an exercise for you. If a square is even, a must be even. Okay, so with this, we start with a is even, okay? If a is even, a can be written as 2k for some k, right? Okay, so a is even, and a can be written as like 2k. Now I go back to this guy. 2k square is equal to 2b square. 4k square is equal to 2b square. This implies that 2k square is equal to b square. That implies that b square is even. And it implies that b is even. Well, now we concluded that a is even and b is even. Well, that means a and b have a common divisor, right? But our assumption was they should not have a common divisor or divisor, okay? So, hey, a over b cannot, so we contradicted the assumption that square root is rational and represented as a over b is not 0, and a and b are in the minimal representation. So that's a contradiction. Here, this also explains the same thing. Sometimes you can disprove a statement by using a counterexample. As long as you can come up with an example which contradicts with the statement, then you can disprove that statement. For example, prove or disprove that product of two irrational numbers is irrational. So that's the statement. We say product of two irrational numbers is irrational. That is P, okay? Well, I can easily show that. Think about two irrational numbers. For example, square root of 3, okay? And multiply it with another irrational number, square root of 3, and then you get 3, right? This is irrational. This is irrational, but this is rational. So product of two rational numbers is not always irrational. So we had a counterexample that this statement is not true. Okay. All right. So here is an example. Prove the proposition P0 is true. How do we show that proposition P0 is true? And P of n is the proposition if n is a positive integer greater than 1, then n squared is bigger than n. So basically, if n is bigger than 1, okay, then n squared is bigger than or equal to n. This is P, this is Q. That means P implies, sorry, let's not call it P. It's going to get you confused. So let's call this one X. Let's call this one Y. That means X implies Y, okay? P is X implies Y. So, well, what about P0? This is propositional function, right? What is P0? P0 is if 0 is bigger than 1, then 0 square is bigger than or equal to 0. That's the statement that we are trying to prove. But look, this is false, right? Remember, if P is false, no matter what Q is, the P implies Q or X implies Y must be true. That was vacuous proof, right? So that is what we do. The proposition is vacuously true because 0 is not a positive integer. So if you have biconditional statements, in order to prove a biconditional statement is true, you have to show in both directions. For example, remember P bidirectional, biconditional Q. In this one, you have to prove that P implies Q, and you have to prove that Q implies P, okay? So if you have a statement like if and only if, you have to prove in both directions. Here is an example. Prove the theorem if n is an integer, then n is odd, if and only if n square is odd, okay? So here, n is odd, that is P, this is Q, if and only if, okay? So in order to prove n is odd, if and only if n square is odd, first you are going to prove P implies Q. In other words, you are going to say n is odd. That will imply that n square is odd. This is pretty easy, right? If n is odd, we already proved that 2k plus 1, n square will be what? 2k plus 1 square, which is 4k square, plus 4k plus 1, which is 2k square plus 2 plus 1, and this is r, that means 2r plus 1. So we prove this side. The other side will be Q implies P. You will start with n square is odd, okay? And then you're going to prove that n is odd, okay? If n square is odd, I'm going to leave this an exercise for you. This is trivial. You can also prove that. So the point here is if you have if and only if, you have to prove in this direction and you have to prove in this direction. Okay. Here is another example. N is odd if and only if 5 plus n is odd. So here, this is your P, if and only if, this is your Q. So what are you going to do? You are going to first assume that n is odd, and then you're going to show that 5n plus 6 is odd, okay? That's trivial. If n is odd, n can be written as 2k plus 1, 5n plus 6 will be 5 times 2k plus 1 plus 6, and anyway, so you can end up with a statement like 2 times r plus 1. So that means if n is odd, 5n plus 6 is odd. That's obviously true. And then you start with Q implies P. That means you assume that 5n plus 6 is odd. And then you're going to show that n is odd, okay? And here, first, you're going to show that. How can you show that? Well, you can use contraposition, right? Contraposition, what was it? What was contraposition? So in order to prove Q implies P, you can show P naught implies Q naught, right? They are equivalent. P naught implies Q naught. In other words, you can say if n is even implies that 5n plus 6 is even. If you can prove that, that's equivalent. So now I'm going to start with n is even, 2k, 5n plus 6 is 2 times an integer, so that means this is even. So we prove that P naught implies Q naught, that's equivalent to Q implies P, okay? So that's pretty simple. That concludes this short lecture. Here, actually, we didn't do a lot, and we introduced different ways of proving mathematical statements. You can use direct proofs or indirect proofs, and we focus on contraposition and also contradiction. And also you can come up with a counterexample to disprove a statement is true or not. So this concludes the foundational topics, basically logic and proofs. This was a brief introduction with a series of 5 lectures. And during the semester, we're going to come back to proofs and show you how you can prove by induction, which is a very commonly used methods, especially when you deal with integers. Okay, I'll see you in the next video.